Well, hello everybody. In this screencast, I want to take a look at limits just from one side, not from both sides, just from one side, hence the name one-sided limits. So consider the following, Bill Nye the Science Guy. We've got some function. This is f of x is radical x squared minus 1. And this is 1, and that's negative 1. And we might try to talk about the limit of this function as x approaches 1. And that would be the limit as x approaches 1 from either direction. So you'd be looking at things coming this way and say, sure, that's 0. And you'd be looking at things coming from, well, where do I even draw the arrow? Like, there's nothing here. And since there's nothing here, we can't talk about the limit as x approaches 1, but we can talk about the limit as x approaches 1 from the right-hand side. The plus indicates that we're coming from the positive end of things. The limit as x approaches 1 from the right-hand side is 0. We don't talk about the limit as x approaches 1 from the left-hand side. Similarly, we could talk about the limit as x approaches negative 1, and we'd have all sorts of issues. Because we could talk about how things are coming this way, but we can't talk about how things are coming from the right. So we could talk about the limit as x approaches negative 1 from the left, and as we approach from the left-hand side, those values get closer and closer to 0. These are what we call one-sided limits. They are one-sided limits because they have this superscripted negative sign or this superscripted positive sign. They only take into account one way or the other, not both. There's a theorem. It's a fairly important theorem, and it goes like this. The limit as x approaches c of f of x is L. If and only if the limit as x approaches c from the right is L, and the limit as x approaches c from the left is L. And this is that idea that we've talked about in times past. If from the left and from the right you're approaching different numbers, there is no limit. But if from the left and the right you're approaching the same number, then we have a limit. So here's a quick picture for you. This is some function f that I made up right off the top of my head. And I'd like to consider some things about this function f. I would like to find the limit as x approaches 1 from the right of f of x. As x approaches 1 from the right. Well, there's 1. So as we approach from the right-hand side, we're coming this way, and the y values are getting closer and closer to 3. But if we ask the question, what is the limit as x approaches 1 from the left-hand side? Well, as we approach from the left-hand side, there's 1. As we come in from the left-hand side, okay, jump on the train. The y values are getting closer and closer to 0. Which leads us to conclude that the limit as x approaches 1 of f of x, well, what would that be? Well, that would be the number that the function f is getting closer and closer to as x gets closer to 1. And you think 3, 0, 3, 0, 3, 0. But they don't agree, so it's DNE. We say that the limit as x approaches 1 does not exist. Similarly, we say the limit as x approaches 2 of f of x. Well, there's 2. As we approach from the right, that limit is 1. As we approach from the left, that limit is 2. And so that is another limit that does not exist. And you could very easily, with your roommate right there, make up some other examples. Limit as we approach -2 from the left or from the right. Limit as we approach -1 from the left or from the right. Those are some things you should probably play around with. Let me do a quick triggy thing if I can. We have talked in classes past about how this limit is 1. It actually popped up in one of our in-class activities where we talked about the limit of sine theta over theta being 1 as theta approaches 0. This is, of course, for theta in radians, which is the only way cool people measure angles anymore. I would like to give you a little bit of a proof of that without getting too weird. I'm going to take a piece of the unit circle. This is a unit circle. It's a circle of radius 1. This is going to be some point 1, 0. I'm going to drop a tangent line here, and I'm going to pick some random angle theta. This is a random angle theta. That point's going to be called P. This point's going to be called T for tangent. I'm going to drop a perpendicular here to some point Q. So we're all clear. This is a unit circle, so that's 1. That radius OP is 1. You down with OP? Yeah, you know me. Some things you should remember from trigonometry class. This is sine theta. This is cosine theta. Sine squared theta plus cosine squared theta is 1. This length is tangent theta. And what I'd like to do is I'd like to compare the sine of theta to theta itself. And I'm going to do that by making use of an inequality and a little bit of the squeeze theorem. So here's what we know. I'm going to zero in on sector OAP. That's this sector. It's a part of a circle. Now, you and I can agree that that sector has a bigger area than triangle OAP. Could you not? The blue sector has a bigger area than the red triangle. And you could also agree that triangle OAT has a bigger area than either of those. Can I get you to do that? Super. Well, let's do a little bit of algebra. The area of OAP, this is the area of a triangle, so that's 1/2 base height. And the area of the big triangle, OAT, well, that's 1/2 base height. And the sector, well, the area of a sector is 1/2 times theta times r squared. That's something we should remember from pre-calculus. So, a little bit of interesting algebra here. We're going to divide everybody by 1/2 sine theta. And 1/2 sine theta won't be 0 because theta is in quadrant 1. So when that happens, we get 1 is less than theta over sine theta, which is less than 1 over cosine theta, and I'll give you some, so you can hit the pause button if you don't know that that turns into 1 over cosine theta. Now, I'm not interested in theta over sine theta. I'm interested in sine theta over theta. So what happens? Well, we take reciprocals. Reciprocal is easy here, reciprocal is easy here, reciprocal is easy here, and when we take reciprocals, the sense of the inequality reverses. And then I'm going to apply a theorem that we learned a couple days ago. We're going to look at this sandwich theorem. What happens to this as theta approaches 0? Well, the cosine of 0 is 1. This is 1, and this gets closer and closer to 1 as theta approaches 0. Therefore, as theta approaches 0, our guy that's stuck in the middle with you also has to go to 1. Technically, this is a limit as theta approaches 0 from the right, because the only thetas we're considering are first quadrant angles. So technically speaking, it's a limit as we approach 0 from the right, but we can get rid of that because we know that sine theta over theta is an even function, and so the y values work out just fine on both sides. And so this turns out to be too legit to quit. Hey, hey. The reason we do that is because it's a very popular question in calculus. No, not yet. It's a very popular question in calculus textbooks to ask people to compute the limit as theta approaches 0 of the sine of 5 theta over 5 theta. And you would say to yourself, wait a minute, that angle is the same in both spots, so that's still 1. That's still 1. And then it's an equally popular question to ask people, what about that? And I will leave it up to you to confirm for yourself that that's 5/6. That's the kind of thing that you may want to know how to do, and if I were giving guidance on that, I would have you look there. I argue that this is the secret to that number. Okay, so that's between us, and our 12 minutes are about up. There's one more thing in this lesson. It's on continuity, but we'll do that in another screencast. Thanks, everybody.